So let's move to the next speaker. Is Ryan Hofmann. He's going to talk about acoustic waves in ALMA, an epoch analysis. Ryan, the stage is yours.
All righty. You all see it?
Yes.
Awesome. So, yeah, this is just going to be talking about the stuff that I've been up to recently, working with Kevin Reardon over here at NSO, and specifically looking at the sun's atmosphere, the waves that propagate through that, and the ways that we can try to leverage those waves to help us understand both ALMA and the solar atmosphere. So let's get into it. So just a quick refresher, I'm going to go through this introduction fairly quickly. The chromosphere is the middle layer of the sun's atmosphere. It's where a lot of interesting physics happens. The density drops, temperature rises, magnetic field becomes more important, drives the structure and dynamics. There's all sorts of waves and shocks and all of this stuff that we really, really want to understand, because the stuff that happens in the chromosphere is very closely linked to a lot of important problems, like where does the energy come from to heat the solar corona? How exactly do flares and CMEs form and behave? How can we improve our space weather forecasting, et cetera, et cetera? So traditionally, we've studied the chromosphere with spectral line observations, which gives you, depending on the opacity of the spectral line, a more opaque wavelength, doesn't see as deep. So spectral lines can actually give you information at different heights in the solar atmosphere, which from that you can infer things like the line of sight velocity, the magnetic fields, the temperature of the gas along your line of sight. But it's hard, especially the temperature. We try to infer these things usually with some form of inversions, which is just take the observed data, take a guess, a physical model atmosphere, make a synthetic spectrum from that, compare the synthetic spectrum to the observed spectrum, tweak your model, and iterate until you get a model that produces a synthetic spectrum that looks like your observed spectrum. That's problematic and difficult. There's a lot of complicated and poorly constrained mathematics that goes into this radiative transfer, especially in non-LTE. So in the chromosphere, where the intensity, the amount of light you get at a given spot depends not just on the properties of the gas at that spot, but also on more distant regions, either lower down or higher up or to the sides, and that makes the problem a lot more difficult in a mathematical and computational sense. So ALMA turns out to be really useful for addressing some of these issues, because since in the solar chromosphere, this millimeter wavelength radiation is mostly formed from free interactions, thermal bremsstrahlung. It's formed effectively in LTE, so it more or less acts like a linear thermometer, as they like to say. So if you're looking at a certain spot on the solar disk, then in theory, that should just be directly telling you the temperature of the electron gas at that spot, in theory. Now, of course, reality is more complicated than that, largely because the radiation that you see from a given spot is actually arising from contributions along a range of heights, from lower down to much higher up along your line of sight. So depending on the variations in temperature, in density, in ionization state, that will affect what layers are actually contributing to that radiation, because the opacity of the millimeter continuum in the solar atmosphere is mostly determined by the number density of free electrons along your line of sight. So where does ALMA actually form? Well, the chromosphere more or less is the easy answer, but to get a better handle on where exactly it's coming from, especially as it varies over time and throughout space, you can try to infer that using wave propagation. So there's these acoustic waves that are produced by the convective motions lower in the sun's atmosphere. And those acoustic waves propagate upward, and as the density drops, they steepen and eventually form shocks higher up. And so since we know the sound speed more or less in the solar atmosphere, it's roughly 7 kilometers per second in the chromosphere, then you can use observations of 2 different diagnostics at a given point over time. And if you can see a given wave propagating in both of those, then you can get a time lag. And from that time lag, you can infer a physical separation, as has been done with spectral lines, say iron 7090 and calcium 8542, among many, many others. So if we can see these waves in ALMA and observe them as well with a spectral line that forms in a similar region, then we can do the same thing. This has been done sort of by other teams. For, say, Chai et al. 2022, looking at the core of a sunspot and observing the propagation of umbral oscillations, specifically comparing temperature oscillations they see in the ALMA band 3 with the velocity shifts of the H alpha line. But in the quiet sun, it's a little bit more tricky because except for really, really quiet regions, previous studies suggest that these oscillations tend to be either obscured or otherwise suppressed by the structure of the magnetic canopy, where you have these tangential components to the magnetic field. And so whether you're just getting your line of sight blocked by an overlying fibril of dense gas, or whether it's just suppressing or redirecting these oscillations at the 3-minute frequencies. So I'm not gonna go into that too much, but the basic thrust is that if we look at an actual time sequence of these ALMA observations of the solar atmosphere and have a simultaneous observation of, say, the line of sight velocity of spectral lines, then we can try to attack this more directly. So these observations were taken in December 2018. We have the iron 6173, which is low in the photosphere. Then we have potassium 7699, which is higher up a little bit. 8542, which is a calcium line in the low chromosphere. So now you're starting to see those fibrils and where you have these overlying horizontal fields and where it's more open and you're more likely to actually see these vertically propagating waves. And then of course H alpha, which is pretty much all these fibrils and high lying gas. So looking at the time series, you can see in this sequence of calcium 8542 spectra, this characteristic sawtooth pattern, which is the signature of these steepened acoustic waves or shocks. So it rapidly blue shifts and then slowly red shifts, rapidly blue shifts, slowly red shifts, and so on. And you also see oscillations in the brightness temperature in the ALMA band 3 observations. But the question is, are they directly related to these velocity oscillations in the calcium line? So to figure that out, we use what's called epoch analysis. So we identify the waves in the calcium velocity signatures using the moment of strongest, most rapid, sorry?
3 minutes.
2 minutes, okay.
3.
3 minutes, okay. So we identify all of these waves in the calcium velocity signatures, and you can see their distribution here. Like I suggested before, you don't really see much of any of them in the actual network regions. They're mostly concentrated in the quiet areas, and they have this sort of modeled distribution. And for each of these identified waves, you search the nearby time range in the band 3 temperature oscillations for a suitable counterpart and use the time difference to determine the height separation. And this is just illustrating the basic methodology behind that, using Fourier cross correlation to get the phase shift. And this is just a demonstration showing that this method works using 2 spectral lines. So preliminary results indicate that it's not nearly as simple as we might have initially hoped. While we do find a good counterpart for most of these waves, the time shifts seem to vary widely, suggesting a very wide range of formation heights of the ALMA radiation relative to the calcium line. So whether that's indicating that the formation height of the ALMA is just changing so much, or we also looked at checking the null hypothesis, which is basically instead of testing if calcium wave, then ALMA wave. We look for if no calcium wave, then no ALMA wave. And actually, it turns out that that is not the case. And in fact, there are many locations where we're seeing these 3-minute-ish ALMA temperature oscillations where there's no waves occurring in the calcium line. So maybe it's just the case that the band 3 is just doing its own thing and doesn't necessarily care about what is happening down below with or wherever the calcium line. But there is another potential avenue, because we got not just band 3 data, but also band 6. And in the band 6 data, which forms a little bit lower down than the band 3, we see significantly stronger temperature oscillations, whereas the band 3 temperatures varied by maybe 200 or 300 Kelvin up or down above a mean. Here we have variations about twice as strong as that, and also a much more significant peak in the total power spectrum around this 3-minute period window. So, and this is kind of interesting initially, because this was also predicted by analysis of simulations, which found that the band 6 should, in fact, more or less sort of ride the leading edge of these steepening waves and more strongly respond to the to these shocks, these temperature oscillations. So it'll be interesting in coming days to see what happens when we do this same sort of epoch analysis, but with the calcium line velocities simultaneous with the band 6 data. So we'll see what happens. In summary, time domain ALMA observations of the sun are useful, but they're also frustrating. It's a very complicated and messy problem. The sun's atmosphere is complicated and messy. And well, at least we tried, is, I guess, the basic takeaway. So with that, I will take any questions.
Thank you, Ryan, for this really interesting talk about the sun. I have to confess that it's probably the first one that I hear about in my career. So thank you very much. We have a question from Abhijit.
Yeah, hi. Thank you so much for the great talk, Ryan. I was wondering whether you can gain more information by looking at the sort of lower resolution ALMA data and slightly higher resolution, whether you can pinpoint where the emission is coming from compared to the CA line, or whether that's not too helpful.
So the limiting factor there really is the resolution. And for these observations, the reconstructed beam size of the ALMA is about an arc second, give or take, which is similar to the granule size on the sun. I'm not sure that we can really. So this was about as high resolution as we could get at the time these observations were taken in the configuration that ALMA was in. And fundamentally, the resolution you can achieve is limited by your maximum baseline and how you sample in UV space and then reconstruct it. Jonathan Stauffer, one of my colleagues, could tell you much more about that.
Yeah, unfortunately, for the solar observation, you don't get the full 16-kilometer baseline available. Otherwise, that would have been really fantastic.
It would also be really fantastic if we could have simultaneous observations in band 3 and band 6, but apparently that's too difficult to calibrate and set up and everything.
Thank you so much.
Yeah.
Okay, we have to move to the next speaker. So if you have a further question for Ryan, please use the Slack channel for